Okay, welcome everyone to my continuation of what is algebraic graph theory. Today I would like to talk about symmetries and graphs. So symmetries of random graphs, it's kind of the formal title. But I actually really want to talk about kind of symmetries in general, if you want. And the point again will be that somehow for graphs, everything is somehow so easy that you can actually write down a proof for statements that are pretty obvious, right? The usual problem with mathematics is even things that are pretty obvious are sometimes really hard or really difficult or even impossible to prove formally. And we kind of go to this playground, this toy model of graphs, and kind of do it in the toy model of graphs. And it turns out, and this is kind of very strange and somehow a general flavor that you see everywhere in nature, no, maybe not in nature, in science and mathematics, is that things that are reflected in nature are not necessarily very common in mathematics. So nature is very symmetric. Not like just if you just take yourself, you have a very nice mirror symmetry around the middle axis. I'm just too ugly for me, the mirror symmetry doesn't quite work. But anyway, so usually certainly the human body has a lot of symmetries. And we like symmetries. If you look at buildings or whatever, things we create, they're usually very symmetric. And kind of we are quite offended by an asymmetric thing. But turns out that there are essentially no symmetric objects. And that's what I would like to discuss here. But before we can get started, I kind of would like to recall, explain, probably more recall, because it will be a little bit shortish in the sense of explain. But anyway, so there's this old idea of an object being symmetric, being captured by a group acting on it. So the object I have here is, I guess, a sixagon, a hexagon. And let me just say, the F in the hexagon doesn't exist. The F in the hexagon is just to illustrate what's going on. So usually you wouldn't see a symmetry as a group action such that you don't see a change. So in all those pictures, there are 12 of them, the underlying hexagon stays the same. But in order to, as I said, in order to illustrate what's even going on, we kind of need to break the symmetry, and I put an F here because an F is actually a very asymmetric letter. Anyway, so there's a do nothing operation, and then there's a rotation that I call R by 60 degrees. So you have R, 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 and 5 times R. Yeah, whatever. And you have a reflection symmetry. Well, you can see it here. So this is reflection, this is rotation. And then you can reflect and rotate, do the same. It's like something like this, right? You go to here, here. So this direction is always rotation, with the connection going a little bit like this, which is a bit annoying, but anyway, going a little bit like this. And this one is the reflection. And these are old symmetries of the hexagon. And what you would say here is that the symmetry group of the hexagon, in this case, is a dihedral group with 12 elements, because it just kind of acts here on the hexagon. And symmetry is such a basic concept of nature. As I said, like take yourself, you are very symmetric. So we kind of want to measure that somehow in mathematics. And what people did a long time ago, and it was kind of well known for a long time, that symmetry is very important. So that statement was certainly known for a long time. But anyway, that symmetry is measured by groups that came a little bit later, and the groups are called the symmetry groups of that object. So essentially the automorphisms that keep the properties of the object fixed. And I just want to do exactly the same in the land of graphs. So instead of having rotations and reflections on really geometric objects, I look at more abstract things on graphs. So here the automorphism group of this graph is S5, and I leave it to you to figure that out, actually, why I have the certain drawing here, which actually explains that the automorphism group is S5. So symmetric group in 5 letters. And automorphism is just all bijections that preserve connectivity, that preserve adjacent edges, adjacent vertices, because that's the only property a graph has, right? A graph is defined by being a set with things being adjacent. So what could be a symmetry of a graph? Well, it's an automorphism, so a set map such that connectivity stays the same. And the slogan is somewhat the larger the symmetry group, the more symmetry it has. So let's think about the circle. The circle has a lot of symmetries. For example, you can rotate it by an arbitrary angle. So the symmetry groups contain at least something like all rotations of two space. There's already infinitely many. And of course, the circle is very symmetric. So large symmetry group means symmetric, very symmetric objects. And the question is that we are trying to ask here, or are trying to answer and ask all the time in this random graph theory is, what about most graphs, right? If you draw out a graph or put all graphs in the back, draw out one randomly, what is the symmetry group? How symmetric is actually your graph? So for example, this guy is really symmetric. You can just eyeball that. It's obviously really symmetric. Or you can just say its automorphism group is really large. It's S5, which has 120 elements. You might say 120. Anyway, it's very large compared to the number of vertices, which was 10. And so it's a very symmetric object, and it kind of works, as I said, you can just eyeball that it's very symmetric. But if I draw some graph like this here, this doesn't look very symmetric to me. And it probably has a very small automorphism group. Anyway, so symmetries are everywhere, right? Symmetries are everywhere in nature and in graphs. Symmetries are everywhere. Well, maybe not actually. So what you can do is kind of a naive approach. You list all graphs up to a certain number of vertices. My standard approach. That works well for graphs below whatever 20 vertices, and you list their automorphism groups. And well, you just make a list and see what groups turn up. And it turns out that essentially all of them, so like almost all of them, have absolutely trivial automorphism group. And the second observation, so that's kind of observation one. So most graphs are really not symmetric, which is not so surprising if you think about it. If you just draw something randomly, and this is certainly not very random here, whatever. So then this doesn't look very symmetric, right? So kind of random is kind of the opposite of symmetric. So in some sense, most graphs should have trivial symmetry group, and they do. But it turns out, that's maybe the final observation, and actually a pretty cool one, that some symmetry groups appear way more often than others. Some of symmetry groups are really, really rare, and they essentially appear never. So my favorite example is a very small group, Z mod 3, right? That just has 3 elements, but the smallest graph with that group actually has 9 vertices, right? So here we have a group which is really large, and we only have 10 vertices. And here to realize this group, we need at least 9 vertices. And here is kind of a list of those kind of small graphs, large graphs with small automorphism group. So 5 is also very difficult to generate. We need at least 15 vertices for Z mod 5, while something like the symmetric group, as you can see here, is kind of appears very, very easily. It's kind of a strange flavor, and it's not quite clear. So the first one, if you think about it carefully, drawing something randomly probably won't be very symmetric. The second one is a bit more surprising, that certain groups are actually preferred over others. Anyway, so let me do the easy statement first. And the easiest statement is that we fix our usual graph models, and essentially all of them have trivial automorphism group. So almost no graph has any symmetries at all. And so almost all graphs are asymmetric, which is kind of an essence of randomness. So we shouldn't be very surprised that this is true. But the point is, we can just there can be a formal proof. We can make a formal proof here, and it's not just me waffling that this is completely obvious, but you can actually write down a formal proof. And what I find really remarkable, and you can do that in many different settings, so most things actually are symmetric. In some sense, nature itself is not quite random. It looks very random, like life is a roller coaster. Life looks very random to me, but maybe it's not. So somehow asymmetry is always kind of weird. So if you think of something asymmetric, it's always kind of remarkable. And symmetric things, we don't even realize them anymore. Let me make my example here again, with you having a symmetry axis in your face. As I said, I'm too ugly. I don't have any symmetry axis anywhere, but most people should, so you certainly do. So that's kind of weird, right? In some sense, this is saying that nature is not completely random. in a very vague sense, right? There's not any direct relationship between graphs and nature. But I really like this kind of really different than from most things actually super asymmetric, but somehow most things don't appear in real life, which is kind of a weird type of statement. But again, let me draw your attention to this one. It's what we have seen like in the previous videos. We have those graphs and you can do better statements. Here I fix them. Here I fix my probability, for example, and you can certainly do better statements. But let's go to observation 2, actually. Observation 2, so what I did is I randomly generated 10,000 graphs and computed the size of the automorphism groups and listed them. Okay, not surprisingly, I hope by now is that this is 1. So this is trivial, they're asymmetric. Essentially everything is asymmetric. But then you can see that there are certainly biases. So we would kind of factor out those. Okay, we understand those, they're boring. And a lot of groups, a lot of graphs have actually Z mod 2. Some of them have Z mod 4, Z mod 6 for the symmetric group. So this would be Z mod 6 or S3. They appear relatively often. And here's Z mod 8, so a Z mod 2 cube, for example, and so on. So some certain numbers appear way more often than others. And in my 10,000 graph example here, I have nothing with symmetry group of order 3. I have nothing with symmetry group of order 5. I have nothing with symmetry group of order 7, and so on. So here's the precise list in case you care. There was something of symmetry group of order 32, and you could prove that formally. It turns out that the most prominent groups, except the trivial group is by far the most common. Factor that one out. The most common groups are actually already here on the board. They are symmetric groups. So a lot of graphs actually have symmetric groups acting on them, which I find a bit surprising. Or elementary 2 groups, which is also very strange. So something like Z mod 2 to the K, which is exactly the one that turned up here for 32, because 32 is the power of K. And you can formally prove that. It's kind of a very strange bias in kind of what types of symmetries turn up for graphs. And this is somewhat related again to nature. So nature certainly likes 2 groups very, very much. So there's very often a mod 2 symmetry. To really find the mod 3 symmetry, yeah, you need to look. To really find the mod 5 symmetry, you really need to look carefully. Symmetric groups are also very prominent. Anyway, I really like this statement, or both of them actually. The one of them is more like obvious if you think about it. Most things are asymmetric, and we can formally prove that. The other one is, I don't have any really good explanation, honestly, but some groups are just way more prominent, I mean, way more prominent than others as symmetry groups in general, and of course we just did it here for graphs. Anyway, I hope you enjoyed this video, and I also hope to see you next time.